All right, so we talked last time about using Mills methods in naturally occurring situations. So today is going to be a little tougher. This is not going to be, hey, this is all fun day. Each clicker job, though, is going to be asking questions. But it's going to be a little bit tougher for us because there are really two serious issues. Now, there are more than two. I don't mean to imply that this is going to exhaust the possibilities, but there are these two serious issues with naturally occurring data, and one of them is also present with experimental data. One is natural data is messy, right? So we've been talking using Mills methods, and we've implied that all we need to do is look for agreement, disagreement, concatenate variations. We're like, oh yeah, that's all you need to do. But the reality is natural data is messy, and with natural data, one cannot determine causation. Now, one can get suspicions about causation, one can get hints about causation, and in some ways, one might even figure it out. If I were to tell you there's a positive correlation between ice cream sales and people drowning, you probably aren't thinking that ice cream's causing people to die. You might think to yourself, okay, ice cream sales and drowning, what might relate those to? Summer, yeah. So you can't determine, but sometimes it's easier than other to get hints about the issue. Experimental data is messy too. I don't mean to imply that it's not, but so the same policies that are going to be part of natural data are going to be a part of experimental data, and we haven't gotten there yet. So I got to tell you how to deal with messy natural data. Anyone want to take a guess about what class we offer that deals with this? Statistics, yeah. This is statistics. So no, that's very good. Mills methods are good. Data in the real world and experimental data are going to be the same thing, are often not so clear. We often don't have pure agreement, pure disagreement, pure concatenate variation. We have to look for these things. We have to employ statistical techniques to make this work. Now, I am not going to require you to know how to do statistical techniques by hand. I don't do them by hand. And I will go on record, since this is being recorded, as saying I think it may not be as beneficial to have y'all do them by hand as some seem to think it is. Whenever I teach statistics, I show how to do it by hand and then go, a computer will do it. Because see, the issue that I have is that, okay, you can tell me if this happens to you as you're going through the course. By the time you finish the analysis, all of the handwriting, you've forgotten what question you're on and what you were supposed to do. And I think that showing you how the data come, I think is smart, but I've never, ever thought it was good to do them to have to do long, complicated analyses by hand. I don't do them by hand, ever. But I'm going to tell you about four. You're going to have to know these four, what they mean, when you would use them, because that's really more the issue. So there are going to be four main ones. Now, there are other statistical techniques. This is not intended to be exhaustive, but there are four that I make regular reference to. T-tests. We're going to see t-tests a lot. We're going to see ANOVA a lot. We're going to see regression analysis or correlational analysis, depending on which one you want to call it. And we're going to see chi-square. So we're going to see these four. So what I want to do today is I want to introduce you, or perhaps reintroduce you, to four statistical techniques. And since I have it out, if Mose wants to send me coupons, they are free to do so. So Mose, Arby's good. I don't know who's bad. All right. So you are not going to be required, I'm not even going to show you how to do them by hand. Any decent statistical package will, heck, I think, doesn't Excel do a lot of these?
Excel does a lot.
Yeah, I remember when I was trying to learn it, and I would be like on step 13, and I would make a math mistake, and it's like the whole thing's wrong, and I'm like, what was the question again? So I don't do that even when I teach statistics. All right, so I apologize for this coming in now. Apparently none of this wants to come in at the right time, so let's just fix it this way. Get everything in at the same time. If two bell curves were on top of each other, right, so because we're going to deal with data that is usually in the shape of a bell curve. Quite obviously, if two bell curves were on top of each other, they would look identical, and it would be fairly easy to eyeball it and go, yeah, those are the same, because they're on top of each other. In another situation, we would have two distinct bell curves. This would also be very easy, because I could look at these two populations and go, yep, they differ, because their bell curves are distinctly different bell curves. Most of the time, you get something like this. You get something where they're not on top of each other, they're not completely distinct, they're some middle ground. And in this middle ground, we're going to have to use statistical analyses. And what we're going to see is you need to at least know what type of test to use in this situation. So this would be easy. This would be easy. This is less easy. And we got to go, do these two groups differ from each other? Like if these were the heights of males and females, or if these were the IQ scores of two groups. We would say, well, do they actually differ from each other? So I want to introduce you to the techniques on this one. Anyone remember the statistics? What technique would I use? I have two independent groups. What? No, that's more than two. Got two groups. Starts with a T. T-test. Starts with a T, and it's the T-test. So we're going to have to determine if the differences are greater than I would expect by chance alone. Because I don't really expect a situation like this. This would be awesome. But really, I expect them to differ a little bit. And what I want to know is, do these differ more than I would expect by chance? That is, I expect some difference, but are they really, really different? And what I'm going to use here is a t-test. A t-test is the general way. Now, a statistician is probably going to kill me when they watch this, when I go, oh, the t-test is the general way, because they're going to go, oh, do you mean a match t-test? Do you mean a repeat one? Do you mean a one sample? Yeah. In general, if I have two groups, male, female, I'm going to use the t-test. If I'm looking at your height, your weights, your scores on exams, your whatever, I'm going to use a t-test. And the t-test is the most general way to tell the difference between two groups. To simplify the procedure in a way that's going to drive some statistician crazy, what I'm going to do is I'm going to examine whether the mean differences between the groups, so the mean difference is where their peaks are right here, if their mean differences, given their particular variances. I haven't introduced that word, but what is variance? We called it something else in an earlier lecture. I have the mean. What's the variance? It's the spread around the mean. It's how much the data vary. Think variance. It's how much they vary. So you can have a distribution that looked like this, or you could have one that looked like that with a lot more variance. And there's a measure for variance. So what I want to know is, do the means between these two groups, given their variances, spread in the data, and the sample sizes, is that greater than I would expect by chance alone? So with any t-test, you're going to have to know mean, the variance or a measure of variance, standard deviation, and sample size. And what it's going to tell me is there a real difference between these two groups? And that's the t-test. If you want, think two groups. In general, if you have two groups, this is not always true. There are some exceptions. But if you think two groups tends to mean t-test. There's a lot of t's in that sentence. Two groups tends to mean t-test. Two groups tend to think t-test. Oh, that's even better. Any questions about the t-test? Yay! All right, I got more than two groups. The ANOVA. If I have more than two groups, or if I have more than one variable, I am going to tend to use the ANOVA. There are exceptions to this. This is not intended to be an exhaustive review of statistics. But in general, if I have more than two groups or more than one variable, I'm going to use an ANOVA, analysis of variance. The ANOVA is related to the t-test. It's similar. It's an extension of the t-test in some ways, and I know some statisticians are going to go crazy on me when I say that, but it is in some ways thought of as an extension of the t-test. And if you think to yourself, okay, I got more than 2 groups, I need to use a test that's going to look for this, okay, I'm going to use the ANOVA. And this sentence here is somewhat confusing, so I'm going to explain what it means, because it's one of those things that you need to know what's going on. While this is technically a comparison of group to overall variances, what the ANOVA actually tests is you have an overall variance in your group, that is how much they all spread out, like this. And then you have an individual group, the individual group variances. And what we're really testing is the relationship here. And what we want to know, and what we're really sort of under the surface kind of doing is we're saying, is the variances of the individual groups more than I would expect if they were all part of one group? So really, but what ultimately, I realize that's a weird way of saying it, and I'm only going to say it once, because this is not a stats class. What you need to get out of it, though, is what it's going to tell me is this. Well, what does this mean? Little squiggly tilde, what does that tend to mean? No? I guess it can mean approximate. In this case, it means not. So what this will tell me is it is not the case that the mean of group 1, that's this little mu, it is not the case that the mean of group 1 equals the mean of group 2 equals the mean of group 3, etc. So what I get from the ANOVA, and this is the take-home message, what I ultimately get from an ANOVA is that the means vary more than I would expect by chance. I get it in a backdoor way. But if I tell you that if you look at a paper and it says the ANOVA was significant, what they mean is these groups, there is a difference somewhere in the group means. So if I have 4 groups and I run my ANOVA and it's significant, I find there's a difference somewhere. How would I find where that difference was? See, this is where you can start. This is where I think you sometimes get lost in the statistics. This is so great. Let's see if my marker will work. All right, I've run my overall ANOVA. My overall ANOVA is significant, right? You might remember my F, that's the measure I get out of it, is significant, but I want to know where the difference actually is. Right? So this is freshman, sophomore, junior, senior, and I find a difference. What would I do now?
Figure out what the difference is.
How would I figure out where the difference is?
By looking at the variables?
No, okay. If this is more than 2 groups and I have found a difference, what might I do to find the difference in any 2 groups? What test do I do with 2 groups?
T-test.
Yeah. If I find that the F is significant, I can do a follow-up t-test. And that's what you'll see people do, is they get an overall ANOVA that's significant, and then they do follow-up t-tests to see where the difference is. And a statistician is going to go crazy because I didn't tell you they need to control for various factors, blah, blah, blah. This is not a stats class. If what you remember is, if I have more than 2 groups, I need to do an ANOVA and then a follow-up t-test to see the difference in 2 groups, you are probably better off than you were 30 minutes ago. Anybody else blank stares? Seriously, are they like, holy hell.